Welcome to another session. All right, so now let's look at how to solve this question. We have an alpha particle has a range of 250 micrometers in a nuclear emulsion plate. What would be the ranges in the same emulsion of a helium nucleus, which is what we have here, which is that of an alpha particle, and of a tritium nucleus, okay, if they have the same initial velocity as the alpha particle. Now, you know, for for us to know in what range, okay, what ranges in the same emulsion of alpha particle and helium, that's the tritium nucleus. Okay, this is helium nucleus and tritium nucleus. Okay, in what ranges will they be if they have the same initial velocity as alpha particle? Now, when we talk about nuclear emulsion, okay, in a situation whereby we want to find out the ranges in the same emulsion of a nucleus, that's the nucleus of helium and that of tritium, when they have the same initial velocity. Now, the first thing is to understand why we have what we call what we that's to understand the range. Now, the range of a charged particle in a material, okay, can be determined by what we call the stopping power, because when we talk about nuclear emulsion plates, now what we have here is that we have, okay, now what we have here is that we have the ionization of the alpha particle radiation, okay, coming out or emitted from a point source. So when the alpha particle, the ionization of the alpha particle is radiated, okay, the emission plate will now what? Will absorb the energies, okay, possessed by the radiation, okay. So when these energy are absorbed, okay, during the nuclear emission, then the radiation will be what? Will become scattered. So because as the um, as the as the radiation, okay, emanates from the point source, okay, now it's going to what? It's going to decrease with the distance at which it travels. What I'm saying is that when we talk about, let's say this is the alpha particle, and I mean this is the point, we have the point source emitting, okay, ionization of alpha particle. So we have the emission plate placed, okay, along a path, okay. So which means when the emission plates, okay, are placed along the path of the ionization of alpha particle radiation, now two things will happen. Now the first thing is that there will be what? Absorption of, there'll be absorption of the energies. Okay, there will be absorption of energies of the charged particles. Energies of the charged particles. Now, the charged particles in this case will be the what? Alpha particle, which is represented with as the what? Helium nucleus, and also the tritium nucleus. Okay, so like I said, the radiation, okay, will travel across, it will travel through the what? A medium. And when it travels through the medium, okay, the emission plate will absorb the energies, okay, the energies possessed by the ionization of the alpha particle radiation. Because we know that now, when we talk about what we call stopping power, stopping power measures the rate at which the energies, okay, the energies of the charged particles, okay, are absorbed, okay, are absorbed by a material during what we call nuclear emission or nuclear emission. Okay, so now to now find out in what range in the same emission of helium nucleus and tritium nucleus can we have this to have the same initial velocity. Now, first of all, now when we talk about stopping power, you know, stopping power, okay, can as well be explained, or like I said, the range of the charged particles in a material can as well be explained or be determined by what we call energy loss. Now, the energy loss by the alpha radiation, okay, coming out from a point source or emanating from a point source, okay, will depend on the charge of the alpha particle, and also depends on the velocity, okay, the velocity at which it travels. So, but in this case, when we talk about range, now, when we talk about range, okay, so we have the range of alpha particle, which is what we are given here to be 250, okay, we have 250 micrometers. Now, then we know that the charge on alpha particle is what? Plus 2. So for the alpha particle, the charge on alpha particle is plus 2. Okay, and also we know that the atomic mass of alpha particle, the atomic mass of alpha particle is 4. This is the atomic mass, and this is the what? Atomic number. Now, that is the information we have for alpha particle, okay, regarding this question. Now, the range for the tritium nucleus. For the tritium nucleus, okay, for the tritium nucleus, we are looking for the range. That is the unknown value. We want to find out in what will be the range, okay, the range between alpha particle and the tritium nucleus. Okay, so we know that of alpha particle to be 250 micrometer. Then for the tritium nucleus, that is the one we have to find out. All right. Now we also know that the charge on the tritium nucleus is plus 1. Okay. Tritium is one of the isotope of hydrogen. So we have that to be plus 1. Then the atomic mass of tritium, okay, the atomic mass of tritium is what? Is 3. The atomic mass is 3, which is also known as the neutron or the mass number. The mass number, actually. So now, to now find out, now what is now the relationship between range and atomic mass with respect to what? Charge. Now, range, the formula for range. Now, range is related to the charge on a charged particle and its atomic mass by the formula R proportional to the atomic mass of a charged particle, okay, and it's also inversely proportional to the what? To the charge, okay, the charge on the particle raised to the power of what? Of 2. So this is the formula, okay. This is the mathematical analogy, you know, telling us the relationship between the range of alpha particle or the range of a charged particle, okay, and its atomic mass with respect to the what? The charge on the what? Charged particle. Now, one thing we must know here is that when we talk about stopping power, like I said, stopping power also measures the force of retardation acting on a charged particle, such as alpha particle, beta particle, because when we talk about radioactive decay or charged particle during radioactive decay, we have alpha particle and beta particle, okay, and this happens when there's an interaction with matter or with bodies of matter, and that will result in what we call energy loss. Okay, so that's when you want to understand why we have stopping power, because here the the what we call the ionization of alpha particle, alpha particle have high ionization ability. So the ionization of alpha particle, okay, the alpha particle radiation which emanate from the point source, passing through the what? Passing through the material, okay, will suffer what we call energy loss. So this energy loss it suffers, okay, would be, we have the energy loss, to be proportional to the charge on the what? The charged particle with respect to the what? The square of the velocity of the moving charged particle. So that's when we talk about what? Energy loss. Okay, that's in the case of energy loss. So that's now, so this will also help when it comes to how to calculate energy loss. Okay, but now what we are dealing with is what? Range. So I'm going to what? I'm going to write the ratio of the range, that of alpha particle to that of what? Tritium nucleus. Okay, and to find this ratio, we're going to have the what? The range of alpha particle, which is 250 micrometer. Then we divide it by what? The range of tritium nucleus, which will be equal to, remember I said atomic mass of the charged particle divided by the what? The charge possessed by the charged particle. Okay, so now for alpha particle, since we have alpha particle ratio tritium nucleus. So for alpha particle, the charge is what? The atomic mass. Okay, the atomic mass is 4. Okay, the charge on alpha particle is what? 2. So we raise that to the power of 2. Then divide by, okay, divide by, so for the tritium nucleus, we then have the atomic mass to be what? 3. And then we divide it by what? We now divide it by 1 square, because the charge on tritium nucleus is 1. So in this case, this is 4, and so 4 we cancel 4, so we left with 1 here. So this will be 250 micrometer over the range for the what? The tritium nucleus. The range for the tritium nucleus equals to 1 divided by 3, because 3 over 1 square, that will be 3. Okay, so this same thing as 1 over 3. So we are going to have 250 micrometer to be equals to, that's over what? The range for the tritium nucleus to be equals to 1 over 3. So when we cross multiply, we are going to have the range for the tritium nucleus to be 3 times that of alpha particle, which is 250 micrometer. So we can see here that the range of tritium nucleus is 3 times that of alpha particle. So this is going to give us 750 micrometer. Therefore, we are going to have the range, because here we have what would be the ranges in the same emission of a helium nucleus and of the tritium nucleus if they have the same initial velocity. So the ranges would be between, the first one is what? 250 micrometer, okay, to what? To the 750 micrometer. That will be the ranges. Okay, now don't forget that this is for alpha particle, and why this is for what? This is for the tritium nucleus. Okay, this is for the tritium nucleus, and that this is the range we are looking for. I believe we've learned something from this. Okay, so now, like I said, do not forget that the formula, okay, that's the formula showing the relationship between range and the atomic mass of a charged particle with respect to the charge on the charged particle is this formula. Thank you. I'll see you in the next video. Bye bye.